All right, this question starts with the idea of defining gravitational potential energy. Do make sure you remember your definitions. So for this one, work done moving a mass from infinity to that point, as it clearly says there. Learn your definitions. Next, you can read that part for part B yourself. Okay, do read carefully. What does it say? R is the radius of Mars, which is 3.3 mm. Be careful there. So we're talking about megameters, so be careful of units. Look at the graph 2, radius in terms of R and potential in terms of megajoules per kilogram. So again, be careful of units. Let's look what's asked. Calculate the change in gravitational potential energy of the rocket at distance, 4r from the center. So obviously we're going to need to use the graph. So we're going to need to use the gravitational potential at the surface and the gravitational potential at 4r. If you look at those values, you can see those clearly there. So you have one and you have the other at 4r, so here. Look again carefully at the scale and you can see those. But it's asking what is the gravitational potential energy, so obviously, and you're looking at the gain in gravitational potential energy, so you've got the change in gravitational potential times the mass, and the mass is clearly stated there. That gives you a final answer of 1.13 times 10 to the 11 joules. Show the magnitude of the gravitational field strength 4 after the center of Mars. Now, remember, for the gravitational field strength, it is the potential gradient that you're looking at, the potential gradient. So, although it's only 2 marks, nasty question, a lot of work for it, because you're going to have to use the gradient of the graph. And that gradient at 4r. So when I've drawn the gradient, what have I done? I've tried to make the gradient as long a line as possible. There's no specific values, but I tried to keep 2 of them simple. So use radius r of 1 and 6, and then I only have 2 numbers. That's a little bit more difficult to read off. Yes, a lot of work. Be careful. Next, what have I done? I've then plugged that into the formula, delta V over delta R. I have to be careful. Why am I multiplying here by 3.3 times 10 to the 6? Well, as you can see, you have R is the radius of Mars, which is 3.3 megameters. So we have to use that value. So that's where that comes in, that 3.3 times 10 to the 6. Work it out carefully. What do you end up with? A minus value. G is usually negative. Do we need to state negative here? No. We can just state 0.23 newtons per kilogram. After all, that is what they've given in the question. And the values there worked out very nicely when I used them. Part C, what are we trying to do? Find the magnitude of the gravitational field strength at the surface of Mars. You've already got the value there. What are we using? Well, we know little g equals F over m. So we know that little gm equals gm over 4r squared. So we're squaring that value, so obviously be careful. What are we doing? We've got 16r squared. And we know that that value comes to 0.23. So what do? 0.23 times 16 comes out 3.68. Very good idea to make sure you've got a value coming out as to what you've calculated it, so you can clearly see that you have made the calculation. What does that come out at? Rounded off, 3.7 newtons per kilogram. Do put your units, even though they're stated up there. Lastly, the easiest question, probably the easiest question that is there. So we're looking at the escape speed. Escape speed to leave Earth is definitely going to be greater. Why? Because the potential at the Earth is so much smaller. We're dealing with negative values, so minus 63 megajoules per kilogram, and it is a more negative value than the value of the potential at the surface of Mars. So a nice easy answer at the end. Thank you.